Yeah, dear students, today I demonstrate another experiment, namely solar cell. You might have seen solar cells on different places. Solar cells are used to generate power from solar energy or the radiation coming from the sun. You might have seen the solar panels erected and installed on the buildings to give power to the domestic supply or to industrial supply. You might have used the solar cell panels to power your calculators, your wristwatches, etc. Today, in this experiment solar cell, we study the VI characteristics of solar cell and also we calculate efficiency and fill factor of solar cell by drawing its VI characteristics. A solar cell is a PN junction device. You have already done photo detectors and photodiodes. And at the time we have seen that these PN junction diodes or optoelectronic devices can be operated either in photoconducting mode or photovoltaic mode. The solar cell is a PN junction diode with zero bias and converts the incident optical energy into electrical energy. The process of converting the incident light energy or optical energy into electrical energy is known as photovoltaic effect. Therefore, solar cell is a photovoltaic cell. And solar cell works on the principle of photovoltaic effect, where the instant light energy on the PN junction converts into electrical energy and thereby produces electricity. And we don't give any biasing voltage here. Whenever the light falls on the solar cell or a PN junction diode, rather it converts the incident light into electrical energy, thereby it itself is a battery. So solar cell is now operated in zero bias and hence it is called photovoltaic mode. In photoconductive mode, we apply biasing like a photodiode. And a solar panel, you have seen a large panel, solar panel, is consisting of large number of solar cells. Each solar cell is a one PN junction diode. Thereby, solar panel contains large number of solar cells which are the PN junction diodes. They are either connected in series or in parallel depending on the requirement. If you want the current or the required current, you need to connect them in series. If you want the required amount of voltage, you have to connect them in parallel. Therefore, series and parallel combination of the solar cells makes the solar panel to design for required amount of voltage or current. Mostly solar cell made by the semiconducting materials like silicon, because silicon has a good window for sun energy. The light energy coming for the sun we call it a solar spectrum, and solar spectrum is very huge. And in that huge solar spectrum, if you could able to utilize maximum wavelengths, then the efficiency of the solar cell is good. And these requirements can be meted by using solar cell made by silicon. These silicons also we use for better efficiency crystalline silicon materials. So if the efficiency is good if you are using crystalline silicon, or you also can use amorphous silicon, but the efficiency is less. But there are now today a lot of materials are found to make solar cells, and the research is going on to generate or fabricate or manufacture new solar cell with new materials that give you good efficiency. Mostly the commercially available solar cells made by crystalline silica or amorphous silica or hydrogenated silicon, they give up to 18% of efficiency. That means we are unable to use most of the radiation to convert it into electricity. Therefore, we have different solar cells, namely dye-sensitized solar cells, quantum solar cells, which are nano-based materials, nano solar cells, etc. Today, a lot of research is going on in India and abroad to find solar cells that are capable of giving a good efficiency as good as maybe 30%. Instead of using a solar panels on a glass substrate, today the solar cells are also available on films. You can roll them and you can stretch them for any length, and thereby you have easy installation. Now, in this experiment, solar cell characteristics, the aim is to draw VI characteristics of solar cell, and from those characteristics, we have to find out the efficiency and fill factor. Now, I demonstrate how to do this experiment using a solar cell characteristic board. Look this one, this is the solar characteristics board. You can see we have a voltmeter, digital voltmeter, we have a milliammeter to measure the current and voltmeter to measure the voltage. And we have a load resistance variable, you can vary the load resistance and thereby you can change the voltage and can find out the current. This is the power switch on and switch off. I have switched it off. This socket is to connect external light source which acts as a virtual sun. We have to do the experiment under sun, but we are doing indoor, therefore a light bulb, this light bulb is used as a sun, and this is the solar cell module. In this module, there is a solar cell inside this hole, and the area of the solar cell we want, and that will be supplied by the manufacturer. So if you make the light to fall on this, then the solar cell generates the electricity. So to do that experiment, I am taking the solar cell 2 points. This is a positive terminal and a negative terminal taken from the solar cell module. And this you can connect as two terminals, output terminals from the solar cell. Now we have to give power to the bulb, and I am giving power to the bulb, to this external bulb, by keeping it in this socket. It is, if I switch on, this bulb will glow. Is it glowing? Can you see this glowing bulb? Okay. So now if I change this, actually the intensity of the bulb can be changed. But right now this is not functional. So therefore I keep this solar cell at a distance here. If I increase the distance, intensity of the light falling on it changes. Therefore, I can do the experiment at different intensities of incident light by moving this solar cell either close to the bulb or away from the bulb. Now I will connect the circuit. Before connecting the circuit, for any solar cell without any bulb, okay, so I have to measure the open circuit voltage and short circuit current at a fixed incident light. Therefore, I am now switch on the bulb here, not connecting any circuit, and I keep this solar one at a fixed distance. Once you fix this distance, the intensity of the light falling on the solar cell inside remains constant. And for this constant incident light, I have to find out how much voltage it will generate when no load is connected. So when no load is connected in the circuit, if you see the circuit diagram here, this is the circuit diagram. This is the circuit diagram. If I remove the load, this is load, then these two terminals are floating. When they are floating, when load is removed, I mean that load is infinity. Then by removing this load in the circuit, I call it as open circuit. If I remove the resistance but connect by a wire, that means with zero resistance, that is called as short circuit. So we have to now measure what is the maximum voltage it can give when no load is there in the circuit. No load in the circuit means that it gives the maximum output. When load is attached, load drags the power and thereby the voltage developed falls down. Initially, I take the output of the solar cell, the two output. See that from the this is the solar cell I am taking, this is the now output of it. I am keeping this at a fixed distance. I am keeping this at a fixed distance. And while doing connections and taking readings, you should not disturb the distance I am keeping here. Now connect these two terminals, output terminals of the solar cell, into voltmeter directly. I am connecting directly to this for a fixed value of intensity and the fixed distance. Distance is fixed means that intensity is fixed. For this fixed intensity, I find out the voltage as open circuit voltage VOC. Now come to the table. First table for intensity 1, I am taking VOC, and from the 1 it is 0.462 volts. I note down that value as VOC, 462 volts. Still I have not started taking readings. I am now measuring only the open circuit voltage and short circuit current, and these two you should measure without making any circuit connections. And later what we do is I remove these two terminals from the voltmeter, connect them across the milliammeter. Now milliammeter is showing it is short circuited because you know that voltmeter is connected in parallel and ammeter is connected in series. When you connect the ammeter in series, the circuit is short circuited. Therefore, during short circuit, current will be maximum. Hence, because there is no resistive path in it. Hence, I write it as 1.17 milliamperes as the short circuit current ISC. So I make a note of short circuit current here in the tabular form as 1.17 milli. This is called ISC, short circuit current. This is VOC, open circuit voltage. Once you did this, means from the beginning of the experiment, without doing any connections, you need to note down VOC and ISC. After that, I just switch off the power given to the board, but I don't disturb the distance between the solar cell and the lamp, because we have already fixed this distance and we have noted down the VOC and ISC values. Now come to here, how to connect the circuit. I am just removing it. I switched off the power. Now I start connecting as per the circuit given here. If you see the circuit diagram here, the light is coming and falling on it. Once we connect the circuit, then we switch on the light, and the positive terminal of the diode is now nothing but solar cell. And you see in the circuit diagram, no battery is connected, means zero biased. But the photocurrent that is passing through the diode, it will keep the diode in forward bias. Okay. Now I take this here, the two terminals. This is positive, which has gone to, he has given here microammeter, but I am using milliammeter. Positive of the ammeter. So therefore, and then negative of the ammeter has gone to load resistance, and load resistance has gone to the diode or solar cell again. That means initially I complete this closed circuit, and I need to add parallelly voltmeter. Anytime I can add parallelly the voltmeter once the circuit is closed. Therefore, I am starting with this and coming to this, to positive of this. And I take another terminal. This is the another terminal wire I am taking, and this wire I need to connect to resistance. I take this one, I go to the resistance. This is the resistance one, and the second terminal of the resistance is nothing but the other terminal of the solar cell. So other terminal of the solar cell, these are the two terminals solar cell. Now across the solar cell I have to connect the voltmeter. So I take this one here, I connect it here. Okay, negative. I just join them like this. Okay, you see, joining. There is a hole here. I'm joining, and I take another one, and you can see there is a hole in this. In this hole, I have to keep this here, and then connect it here again back. So the circuit is connected. Once the circuit is connected, you can start switch on the power and you can start taking the readings. But don't disturb the distance between the bulb and the solar cell, since we have already taken the VOC and ISC values. Yeah, now look at this. I have done the connections. You have seen the connection also, how to do the connection. After connection, I switch on the power and I have not disturbed the distance between these two, so that the solar cell is receiving constant intensity, for which we have made VOC and ISC measurements. Now come to here. If you see the voltmeter, it is showing, I keep this knob, okay, resistance knob minimum. So minimum. Now I note down the corresponding value of V. It is 0.018 and the current is 1.32. So I note down this as 0.018 and the corresponding current as 1.32 milliamperes. And now I adjust this knob to change the voltage. So I'm changing the voltage. Okay, now I have gone very slowly. It's okay, maybe I'm going roughly around 0.1. Okay, I just need to adjust very carefully and slowly, so that, okay, so it's coming slowly to it. Yeah, I keep it around this 0.055, okay, and the current is 1.31. So I take roughly as 0.0548, okay, corresponding value as 1.31. So I have taken this as 0.08, corresponding current as 1.31. Now I adjust again the knob very slowly, okay, so that, yeah, I have got up to 0.8. Now it has increased, and wait until, yeah, I take roughly as 0.1. Okay, so simply if I want to use, increase this slightly. Okay, this is gone. Okay, weight is slow, steady values we have to note down 0.120, and the current is almost same. So 0.120, current is 1.31. Now I increase the value slowly. Yeah, now current is started decreasing very rapidly, and I adjust this to, okay, the value. 1 minute, I'll just going on increasing the value as 1.5. I'll go 0.15. Yeah, because the sensitivity is there, we are not able to exactly fix it, but still you can try and get the value to nearby values. So 0.132, current is 1.3. So 0.13, it is now 0, and the current is 1.30. Now I increase this value to zero point 0.2, and the current is 1.27. So 0.200, current is 1.28, it is showing. Now I increase this to value of 2.5 nearly, sorry, 0.25. Yeah, now see this value, wait it until it gets stabilized. Yeah, it is 0.248 and current is 1.24, so 0.245 we have, and here is 0.125, and then I increase the value slowly to, okay, wait it, I increase this value around 0.3. I'm still increasing. Okay, I just wait until it gets stabilized. Slowly I am adjusting it to the required value, and as it is now around, okay, 2 point,
128.
0.28, yeah.
1.16.
So I am taking 2.80 roughly, and the current is 1.19. 1.19. Likewise, as I am changing the voltage, there is a change in the current, and now I will go for the value maybe around 0.35 or so. So as I am going here by changing this, it is now,
0.38,
wait and see what is the value of it. Yeah, now it is showing 0.366 and current is 0.93 amperes. Now I increase this further, then the current will be, okay, almost I'll go to 4. It is still less. I'm decreasing. I'm slowly and gradually changing the value, and nearly it is 3.89. I can roughly take this as, see this 4.35, and current is point, so 0.435, current is 0.40. Then I increase it further and I'll see how it is changing. Okay, now I am going it slowly increasing, but current is falling fastly. Okay, I'll go for, we have already taken for this, so this is the maximum I'm getting, 0.43, and zero point 0.4 is the maximum current. So you can take some more readings also in between. This is for the intensity what we have taken. And now we will do this experiment repeated for intensity 2. To get the intensity 2, what I do is I change the distance. Now if you look at the setup, if I change the distance here, you know that, okay, I'm changing distance, and if I change this distance as I'm moving away from the lamp, the intensity that is falling on the solar cell decreases. But remember that the efficiency of the solar cell depends on the material you have chosen. Okay, because while calculating the efficiency of the solar cell, we take the solar constant as a constant, which is taken as the power received on the earth perpendicular to the direction of sun per unit volume, and that will be calculated under different atmospheric conditions called as AM0, AM1, AM1.5, etc. and they do this calculation of solar constant over a period. Over a period means through different seasons, different okay weather conditions, and they found out what is the constant. That constant will be taken in the calculations. Thereby the efficiency of the solar cell more or less, okay, majority times depends on the material you are using and its band gap, because you know that solar cell is made by a semiconducting material have band gap. That is the most important to decide the efficiency of the solar cell. Now come to here, I have changed the distance, and once you change the distance, again you have to measure VOC and ISC. To measure VOC and ISC, you need to remove the circuit and measure again directly with this one. But I am not doing it because we have already connected the circuit. Now I take the readings. After completing the experiment, I remove the wires, then find the VOC and ISC values, because I am not changing this distance. It is constant. Therefore, now I change this knob to 0. Okay, I am turning it to minimum mode, and I find out what is the value of voltage and corresponding current value. Now it is showing 0.15 and corresponding value is 0.94. There is a decrement in the current because the distance has increased. Now I adjust this to some other value, okay, as yeah, 0.1. I am okay, it is 0.05, previous is 0.15. Now I am changing this to 0.5. I mean, okay. So around, I'll change this around value of, yeah, 0.053. Current is 0.93. I have noted down these values. Now I increase the value. I am taking in between intermittent values, but when you are doing the experiment, you have to take more readings so that the graph is good and your calculations will be okay matching with the desired values. Now the value is 1.2. Okay, I'll take it as 0 point. It is not stabilizing yet. Okay. So I'll just slightly decrease the value, and we look at this. Yeah, just wait it, and you have to take very patiently the readings. It was now, it is jumping to higher values. I need to take at least one reading. Yeah, you see this. This is 0.143 and the corresponding current is 0.92. Okay, I have noted down these values. Now I'll go to the next reading by changing this value, okay, to some of the value maybe slightly higher than the previous, and I can adjust. You can see the value as yeah, look at this, it is 0.147. okay, now 0.147, current is 0.92. okay, I'll go for the next, and it is 0.174. okay, 170. Current is 0.19.
91.
Then 91. Current is 0.91. I increase this to some higher value, maybe fixing at 0.8. If I still go higher, it is around 0.2, okay, 0.20 I'm taking approximately, current is 0.90. Now I increase this value and see where it is stabilizing. It is stabilizing around 0.253 and corresponding current is 0.85. Now I go to higher value and see the stabilized value of voltage as, okay, yeah, it is 0.31, it is fallen 0.31. Yeah, the fluctuations are there, therefore 0.31 I am taking, corresponding value is 7.3.
0.73.
Okay, 0.73. Sorry. Then I have increased the value further and I will find out what is the corresponding current value. Now it is 0.3, okay, 360 approximately I am taking, current is 0.60. Okay. Now I increase this further and find it out what is the value of voltage and corresponding value of the current. So it is, I have increased this value to maximum and it is showing around 0.401, current is 0.37. I stop here and I need to now measure VOC and ISC. So without disturbing the setup, I need to remove all of these connections. I am removing this connection, removing this, and I'm also removing these two connections because I have to measure VOC and ISC directly from the meters. Therefore, we have this wire coming out of the solar cell having two terminals. For the second intensity, if I keep this two terminals across the voltmeter, I will get the reading as VOC for the second intensity as 0.443. And I remove this, connect them directly to milliammeter, whatever the current is showing, that is called ISC, and it is 0.94. If you see these two, previous one intensity is higher, therefore the VOC is higher, ISC is higher compared to intensity 2, where we moved the solar cell away from the source, thereby the intensity falling on decrease. So it is VOC and ISC. Now we need to draw a graph by taking a, here the graph is here, okay, graph is given here, and I am taking on the x-axis voltage and I am taking I in milliamperes on y-axis. But in general, I am drawing here the same graph, taking here the voltage in volts and current I in milliamperes. Now we'll get for first intensity, higher intensity, the curve something like this. Some points, you plot them and then join them smoothly, something like this. A smooth curve, you join them. Then extrapolate this curve to y-axis and also to x-axis where it cuts. I'm extrapolating. Here you can see that it is cutting the x-axis. On axis y coordinate is 0, means that current is 0. Current is 0 means this is open circuit voltage. And if you go here, voltage is 0, means it must be equal to ISC. Therefore, you can confirm your experimental values from the graph, whether you are getting this value approximately equal to ISC measured value and this approximately equal to VCE value for first intensity I1. For next intensity, we have moved away, that means distance increased, hence the current decreased. Thereby, I'll get here the second curve something like this, some points. And after getting the points, you join the points and extrapolate them to this. Actually, you can draw these values like this. And after drawing these two, you have to find out the maximum area inscribed or maybe taken in such a way that you choose a point on this curve I2. This is a point. It will not be at the center also, because you have drawn it as in a graph. You count the maximum length and also height, and then drop the perpendiculars to x and y axis. Means that you need to find a point on the curve. If you plot from that point and drop the perpendicular to y-axis and x-axis, you should get a rectangle of maximum area. If I take here, the rectangle is very small. If I take here, rectangle is very small. Therefore, you take a point in such a way that we will get a rectangle of maximum area. But in general, to find this, you can use a load line analysis. If you know R, V and I, okay, you know that V is equal to IR, from which you can draw a straight line passing through this. Where this straight line is cutting, okay, this line, that will be actually the point where you have to do it. Otherwise, from the graph we are doing it maximum point, and similarly you choose a point on this curve where if you drop the perpendicular to x and y axis, you should get a rectangle of maximum area. And this is for I2, this is for I1. This is called as VM, the maximum voltage you can draw from the solar cell when load is connected. This is the value when no load is connected. And this is the value of the maximum current, I maximum, when a load is connected. This is the current when no load is there. And similarly for the second also we'll get VM2, and correspondingly I'll get IM2. VM1, IM1 are the maximum voltage and currents for the intensity 2. Okay, sorry, this I should write to 2, because higher the current means intensity is higher. Therefore, I should write this one, I1, I2, VM2, VM1. Now go to the tabular form. We have already measured VOC, ISC. And come to the second tabular form. The second tabular form is this, VOC, intensity 1, we have already measured here. Okay, you note down this value here. For second intensity also, we have here VOC, note down here. Similarly, we have ISC values for first intensity and second intensity, write them here. Then you find the product of VOC into ISC, that is called PL, load output power. Okay, that is in milliwatts because IC is in milliamperes, but you convert them into watts only. What are the value you are getting? Take the product of VOC and ISC. For the first intensity, you will get here. For the second intensity, you will get here. Now, note down VM and IM values for first and second intensities from the graph. We have drawn the graph. You have chosen a point on the curve so that I'll get maximum rectangle, and corresponding values for the first intensity are VM1, VM2, and for second intensity, okay, or of course, sorry, the first intensity it is VM1 and IM1. For the second intensity, okay, it is VM2 and IM2. Then take these values, note down from the graph what is the value of VM from intensity 1 and what is the IM value for the intensity 1. Similarly, you note down the values for second intensity and we'll get VM and IM. Take the input power, that is which is equal to Vm into Im. Again, this is in milliwatts because I is in milliamperes. Now you need to find out fill factor and efficiency. Fill factor is given by a formula which is Pm by Pl. So I write here power, okay, fill factor FF is equal to, from the formula it is Pm by Pl. Pm is nothing but Vm into Im, which we have taken for intensity 1 and intensity 2 from the graph. PL is nothing but VOC into ISC, which we have already measured. So fill factor gives the maximum realizable power a solar cell can deliver. It is not the efficiency, because you know, when load is connected, the load drags the current and the power drops. Without this, how much maximum power it can deliver to the load, that is called fill factor. So you have to calculate fill factor for this intensity 1 and intensity 2, take the average value of fill factor. Similarly, we have to calculate efficiency. You know, efficiency is always output by input. Whatever the mission or whatever you are calculating, the efficiency is always how much output power delivered for a given input power is efficiency. Here output is electrical power actually we have taken, and the input is light output or optical power. So therefore, to find out efficiency, you should know what is the emissive power of the bulb or emissive power of the sun if you are doing the experiment under sun. So we have already given here area of the solar cell for our setup is 3 into 10 to the power minus 4 meter square, and the emissive power E is 10 watt per meter square. Thereby, I write now efficiency is equal to Vm Im maximum realizable, okay, maximum power we'll get from the solar cell when load is there, that is electrical output. Input is light, that is emissive power of the bulb per area, and efficiency is given in terms of percentage. So therefore, from the table, you can calculate efficiency. From this efficiency, Vm Im, product you know it already, Vm Im, divided by E into A. E is emissive power, we have given 10 watt per meter square. Area we have given 3 into 10 to the power minus 4 meter square. If you substitute, you will get the efficiency for intensity 1, and similarly calculate for intensity 2, take the average. In general, most of the cases, the efficiency you are going to estimate for our solar cell experiment is always less than 10. Okay, because the practical value for or theoretical value for a silicon crystalline solar cell is around 18%, but that is theoretically calculated one. Practically you may not get that value, but in our experiment with this bulb setup we will get less than 10 only. Thereby, do the experiment, connect the, without connecting the circuit, find VOC and ISC for a fixed intensity, and then take the readings as I explained, and change the distance from the bulb, the solar cell, and measure the intensity 2, and change the values of voltage, measure the corresponding values of current. Draw the graph, choose a point for which you will get the rectangle of maximum area, and corresponding values will be maximum voltage and maximum current, and then enter the values in the second table, calculate fill factor as Vm Im by VOC into ISC, and fill factor Vm Im by E into A into 100%. E is emissive power, A is area effect. And after taking the average values, write the result. The average fill factor, whatever you are getting from this, you have to write here. Efficiency, the average value, you have to write it as. This is the experiment you have to do.